Hello, everyone. I'm very glad to take the conference of Black Hat, and my topic is about virtualization software fuzzing integrated with AFL, aka American Fuzzing Loop, which is a famous fuzzing framework currently. And this is my agenda. First, I will introduce a little of us, and also I will introduce how we think and how we consider it our fuzzing approach. And also I will introduce the implementation of our solution in detail. And last, I will try to introduce the case study of how we use our fuzzing framework to reproduce the vulnerability of Vietnam. Okay, this is my partner, Jack. Jack has worked 10 plus years in security in Trend Micro, focusing on browser, document, and kernel vulnerabilities. But his legs are badly hurt, so he could not travel with me. Just best wishes to Jack. And this is me. I have worked about 7 years in security in Trend Micro, mainly focusing on the sandbox development and on kernel exploit of Windows, Mac, Android, and iOS, and so forth. First of all, let's summarize the fuzzing approaches towards virtualization software. The first category, I can call it fuzz in the guest OS. The key point is that the researcher or the fuzzer would try to capture the normal I/O requests in the guest VM and try to replay the requests in the guest VM towards the target virtual devices. And during the fuzzing process, the researcher will fuzz the data and cause the virtualization software to crash. So the advantages for this kind of approach is that it is simple, and it asks no more knowledge of I/O protocol knowledge. But the disadvantage is that there is no code coverage, and by design, the fuzzing scope is incomplete. Another category of method is the conformance fuzzing test, which is suggested in Black Hat conference before. The key point is that this kind of method will try to trace the hidden changes of register and I/O memory using the symbolic execution. So the advantage for this kind of method is it can fuzz deeper. But the disadvantage is that there is also lack of code coverage, and the performance would be relatively low in academic. The third part is the code coverage. The code coverage asks the researcher to revealing a lot of open source code or just reversing the binary code as assembly code. So it would cost lots of effort for the researcher. But this kind of method could not be scalable. Even also, this way is flexible. So there exists many attacking interfaces towards the virtualization software, and our solution is focusing on the virtual devices part here and here. So as our approach, we have designed according to 4 principles in our design. The first principle is about portability. As actually we have used customized BIOS open source system as the common format of a virtual disk. And second, we have used the serial port devices as the communication bridge between the VM and the host. The second point is the performance. Because we have introduced the BIOS, actually the BIOS system is much lighter than the guest VM, such as Linux, Windows, and so forth. So the performance of fuzzing could be high. The third principle is that the fuzzing could be direct. because our fuzzing framework is inner the BIOS system, which can direct access the virtual devices. So there's no interference of the device driver layer of guest VM. So the fuzzing could be directed to the virtual devices. And finally, our solution have introduces of code coverage and feedback and control integrated with AFL. Okay, let's see the architecture overview, module by module. Actually, the whole architecture is divided into four important modules. The left part is the virtualization software process, aka VSP. It contains the customized BIOS system, we call it CBS, and also the memory and I/O space operation proxy server, we call it MLPS. The VSP contains several virtual devices such as network, SIGA, and so forth. And the virtual serial port is here. And another important module is the device control client module. It can communicate with the proxy server via the virtual serial port here. And the device control data is formatted, which is suitable for AFL fuzzing. And the AFL related module is outside of the VM, which is located on the host side here. Okay, this is the fuzzing user interface during our fuzzing activity. It's a typical AFL fuzzing user interface. Let's see the CBS customized BIOS system module in detail. Actually, this BIOS system is based on the CBIOS open source product. And we have designed our proxy server inside the CBS. And we have also used the virtual serial port as the communication bridge. Traditionally, any BIOS system have three phases in the whole life cycle. The first phase is the power on self test, and the second is the boot phase, booting to the guest VM operating system. The third one is it will provide basic input and output BIOS system service for the runtime guest VM. Actually, in our fuzzing framework, we should remove the unnecessary boot phase and the BIOS runtime service and just keep the post phase in our design. And in the post phase, we have add our extra code. For example, after the basic detection of physical memory and the setup of hardware, and we will add our necessary device hardware setup. For example, the virtual serial port. And finally, we will run up our proxy server module in a handle loop. Okay, about the proxy server, the main job is it will receive the memory I/O access requests from outside of the guest VM and execute the request inside the proxy server module until the whole process crash. Actually, we have doing some modification towards the interruption mechanism in the CBS customized BIOS system, and we replace the interruption mechanism with the pull mechanism towards the targeting virtual devices and with timeout mechanism. So the main job of the proxy server is it will receive the I/O requests, which could be described like this. For example, it's input byte, input word, input long, output byte, output word, output long, and read write specific address with specific value and length. So the proxy server can process the ML requests like this. Another important module in our design is the device control client. The device control client would handle or read in the device control data, which is formatted, suitable for AFL fuzzing. And I will describe the DCT format later. So the main job of the DCC could be divided into 4 steps. The first step is to the DCC will fork and launch the virtualization software process, and so as to load the customized BIOS system like this. And then the DCC will say hello to the proxy server inside the CBS. And thirdly, the DCC will send the initialization requests to the CBS. For example, it will send the initialization request towards the USB HCI devices like this. And finally, the DCC will pass the DCD data outside of the VM and translate the DCD to I/O requests. Okay, let's see the workflow step by step. At the first step, we will first instrument the target devices of the virtualization software. For example, the target is the USB-related software, virtual devices. And the second step, we will use AFL fuzz to launch the target device, target application, aka device control client (DCC), and then the DCC will read in the formatted device control data and communicate with the proxy server via the virtual serial port, and then the proxy server will receive the request and execute the request inside the virtualization software process. And finally, the AFL fuzz will calculate the code coverage and mutate the device control data for further fuzzing in the whole loop. Okay, let's see the step 1. Actually, this step is to set up instrumentation towards the target virtual devices. For the open source virtual devices such as QEMU, we will use AFL GCC to instrument the target devices at the compile time. And for the virtualization devices which are not open source, for example, VMware Workstation and so forth, we will try to instrument the executable file statically, or we will patch the binary code within the restricted patch range. So this is the step 1 in the whole paragraph, in the whole graph. And as the step 2, we will set up trace and feedback using AFL. Actually, we will use AFL fuzz to launch our DCC application with a specific parameter. For example, T means time for a cycle of fuzzing. It means 90 seconds. And M means memory, reserved memory for the virtualization VM. And I means input folder, which contains the DCD data, and O means the output data, which contains the generated crash file. So AFL fuzz will automatically mutate the DCD data and calculate the code coverage in the whole loop. So this is step 2 in the whole picture. And the third step is to encoding the DCD and read in. Actually, as we know, AFL has integrated several mutation strategy in itself. For example, bit flip, deletion some part of the input file, and splicing some part of the input file, and so forth. So we must encoding or format the IO requests to specific format, so as to be suitable for the AFL fuzzing. For example, take the USB related devices command entry. For example, here we can encoding the command ID as the first 4 bytes in our DCD, and the following is the input buffer here. Sorry. Following is the input buffer here in this rectangle, and also is another item of command ID in the green rectangle, and followed with the input buffer here in the red rectangle. Okay, this is the step 3 in the whole picture. So the first step is to control the device communication. Actually, the CBS module will start up first. It will discover and initialize the virtualization devices and start the proxy server inside it. And the proxy server will start to initialize the target devices. For example, the USB XHCI related devices. And finally, the DCD module outside of the VM will read in the DCD data and communicate via the virtual port to the proxy server inside the CBS. So the proxy server will receive the request and execute the request inside the CBS until the whole virtualization software crash. Okay, this is step 4 in the whole graph. Okay, let's see the workflow in view of AFL. The first step is to use AFL to instrumentate virtual devices inside of virtual software process. And second, AFL fuzz will launch the DCC. The DCC will read in the DCD, and the DCC will fork the virtualization software process and wait for the VSP process. If the VSP process crashes, so the crash information could be notified to the DCC because our system call wait for PID will return. And if the DCC receives the crash information, it will crash itself. The crash information would be notified to AFL. So AFL fuzzing would get the crash information of the DCC and calculate the code coverage of the VSP process and mutate the DCD data and record the crash of the VSP. Actually, there exists several important tips in our practice and experience of activity fuzzing. One important tip is about the instrumentation. Because there exists much virtual devices, and we only care about several parts of the virtual device. For example, if we just care about the USB part, we could modify the make file like this. For example, for every source code, we only care about the HCD xhci.o related source file. If we find this kind of source file, we will use AFL GCC to compile this kind of source file with instrumentation. Otherwise, we will use the traditional CC to compile the source code. But for the virtual devices, which is not open source, we can try to instrument the executive file. For example, for VMware Workstation, we can try to add this initialization and trampoline segment at the tail of the executive file. And for the target code, we will patch the binary code like this. Trampoline function, first we will save the important registers, and then we will call our AFL maybe log related tracing file, tracing function, and offset we will restore the important registers. And then we will fix the entry point of the executive file to point to the initialization code. Another important tip is about multi-process fuzzing. Because as we see, AFL fuzz will launch the launcher process, DCC. The launcher process will launch the target process. The DCC is not instrumented in our design, and the VSP is instrumented with AFL. As we know, the trace info of the AFL is shared across different processes in nature. So the tracing info is naturally supporting multi-process. So we have to do is just two. The first one is we have to remove the instrumentation check in AFL because the DCC has no any instrumentation. And the other is that we have to deliver the crash info from the target process to launcher process. For example, we can use the fork and the wait for PID method, and also we will check the connection of the serial port to check the crash of the target process. As the pseudocode of the DCC, first it will fork a child process. In the child process, it will launch the virtualization software process, and in the parent process, it will wait for the VSP, and if the VSP process crashes, then we will get a special signal of signal. Then the DCC will crash itself inside its process scope. Okay, let's see a real case study. Actually, we have used our fuzzing framework to fuzz the floppy disk controller devices, and we have reproduced the Venom vulnerability. At first, we will try to instrument part of the virtual devices, and we care about the floppy disk control.object using the AFL GCC, leaving the other source code compiled by CC. And second, we will design our input kit file, our aka DCD, like this. It is simple. First, it contains the command ID, the arguments count, arguments list. And to keep the fuzzing more effective, we will try to integrate several different command line, controller command in our kit file. For example, it will contain the floppy disk read, floppy disk write, and floppy disk seek. And also, we will try to passing our DCC. The DCC will pass the input file and it to the ML requests. For example, it means output the port 3F5 with the value 8E with special value and so forth. And finally, we will use AFL fuzz to launch our device control client. Okay, let's see the video demo. This is the bash file to launch the DCC. First, we we will make two pipelines. These two pipelines are for communication via the serial port, and then we will use the BIOS parameter. This means customized BIOS system, BIOS.bin, with the pipeline we have made before. And then we will use the AFL fuzz to launch the DCC ACA test program. Also, we have designed the time for fuzzing cycle with 900 seconds and with memory of 2048 megabytes. Okay, we can see this is the BIOS of CBS. This is the DCC. This is the pipelines for a serial port, and this is our batch file. Okay, we will launch our batch file. You can see the AFL fuzz will launch up. You can see the total crashes, new IDs, favored paths, and count coverage, and map density, and so forth. This is towards the floppy disk controller. Okay, let's see the second video. In this video, we have generated two crashes, and one is unique. And we will try to reproduce the crash using the crash file. First, we will list the crash files here. This file is generated by AFL fuzz automatically. And we will try to run our DCC with the crash file. Output folder, crash folder, specific crash file, and also we will get the segment fault of the virtualization software, aka QEMU. Okay, this is my last page of my PPT. Thank you very much.